Look at an electric vehicle. It handles massive, dangerous amounts of power. But if you take a closer look and plunge down into its internal wiring, the components actually controlling all that voltage aren't giant mechanical levers. They are microscopic. We manage thousands of volts using parts so small you need a microscope to see them. We rely on two specialized tools to do the heavy lifting: the transistor and the thyristor. Take a look at these vintage metal can prototypes sitting on a piece of graph paper. You can see how this technology started as tangible, handheld hardware before we learned to shrink it by the billions. And despite all the complicated math surrounding them, both devices do exactly one thing. They act as electronic water valves. Instead of twisting a metal handle to stop water from flowing through a pipe, we use a tiny pulse of electricity to block or release a massive flood of electrons. To build a valve with no moving parts, we need a very specific base material, a semiconductor. Most of the time, that means we start with raw silicon, a brittle, shiny crystal. This diagram shows exactly why pure silicon doesn't naturally conduct electricity. The atoms lock tightly together in a rigid grid, sharing their outer electrons. Because all the electrons are securely held in place, none are free to move. The valve is essentially permanently closed. We can change that through a process called doping. By injecting a different element, like antimony, into that silicon grid, we introduce an extra electron that doesn't fit into the tight bonds. This creates material bursting with restless, free electrons, ready to flow. We call this N-type material. We can also go the other way. By injecting a different kind of impurity, we create empty spaces within the crystal lattice. These empty gaps act like powerful magnets, eagerly pulling nearby electrons into them. This is called P-type material. On their own, a chunk of N-type or P-type silicon isn't very useful, but when you press these customized materials right up against each other, the boundary between them becomes a microscopic barrier. We can manipulate that barrier to control electrical flow, all without a single moving part. We build the bipolar junction transistor by squishing 3 slices of doped silicon into the bottom N layer is the emitter, the top is the collector, the middle P layer is the base. Without a signal, electrons cannot cross. The current is blocked. Applying a tiny pulse of current into the base changes everything. The barrier dissolves and a massive wave of particles floods through to the collector. Here is the internal map of what is happening. As flow starts, a few electrons get caught in the base's empty spaces and exit the side lead. The vast majority move too fast, swept straight across into the collector. For engineers, that physical sandwich becomes this standard symbol. The arrow shows the direction the power is moving, illustrating how the tiny control signal joins the main flow to create one large output. Using a tiny signal to command a massive flow is incredibly useful. If you vary that tiny input signal smoothly, the massive output mimics it exactly, which is how we amplify sound. If you toggle it fully open and fully closed, you have a digital switch, which is how a computer processes ones and zeros. Modern computers use a MOSFET. If you look at this construction diagram, notice a key difference. The gate control terminal is separated from the main silicon by a thin, glass-like insulating layer of silicon dioxide, completely isolating it from the source and drain. To open a valve without touching it, applying voltage to the gate projects an invisible electric field straight through the insulation. This field acts like a magnet, physically pulling free charges out of the silicon to form a temporary bridge between the source and the drain. This chart maps that relationship. As we increase the voltage pressure on the gate along the bottom, the drain current rises on the vertical side. A wider bridge means more flow. This is a vital improvement. Because the gate is controlled purely by electrical pressure and not a continuous current flow, it generates significantly less heat. This insulation is the only reason we can pack billions of these switches onto a single smartphone chip without it instantly melting. But transistors have a limit. While they are perfect for delicate logic, they are too fragile to manage the raw power of an industrial motor or a city's electrical grid. The heat would destroy them in a fraction of a second. We build a heavy-duty trapdoor by adding an extra layer of silicon, creating a rugged 4-layer thyristor. Its terminals are the anode, cathode, and gate. In its default state, it acts like a thick brick wall against massive electrical pressure, refusing to let anything through. When a quick jolt of current hits the gate, the 4-layer design creates a self-sustaining cycle. Each layer triggers the next, which then feeds back into the first, locking the pathway wide open. Even when you stop the trigger signal, the energy keeps itself flowing. It's essentially a circuit that latches itself on. To reset this latched valve, you must completely cut the main power supply flowing through it. This makes it perfect for alternating current power systems, where the power naturally drops to zero dozens of times every second, automatically resetting the valve for its next use. Whether it is a microscopic MOSFET regulating data inside your phone, or a rugged thyristor commanding an industrial motor, the principle is the same. By carefully stacking layers of silicon, we learned to control massive energy with nothing more than a tiny electrical whisper.